In this chapter, we're going to talk about the properties of solutions. In this video in particular, we're going to talk about how solutions are formed, and then we're going to get into a couple of the properties of solutions, and then we'll talk further about other properties of solutions in some of our later videos. So when we think of a solution, quite frequently the first thing we think of is something in liquid form, and especially in earlier chapters we've dealt a lot with aqueous solutions. But really, we can have solutions made up of any of the three states of matter. So for example, we can have something that's made up solely of gas, so something like air, where what's dissolved in the solvent is a gas, and the solvent itself is a gas, so the entire solution is a gas. Liquid is something we commonly think about, and we think about solids being dissolved in liquids, but we can also have solutions that are all solid. So something like brass is a homogeneous mixture, which meets the definition of a solution, but it's a homogeneous mixture of solid particles. So we can have a solid solution, a liquid solution, a gas solution, or we can have solutions that are some mixture of those different states of matter. So when we think about a solution, well, how do we actually make a solution, and how do we know whether certain things will form a solution? Well, there's really kind of three steps to forming a solution. The first thing we have to do is overcome the intermolecular forces between the solute particles. So for example, if we have an ionic compound that we're dissolving in a liquid, then those ionic compounds have an attractive force between the positive cation and the negative anion, and we have to overcome that attractive force and break those ions apart. Then, at the same time, our solvent intermolecular forces have to be overcome. So for example, if we're trying to dissolve an ionic compound in water, water we know has strong hydrogen bonding, so we have to overcome some of those hydrogen bonds so that the solute particles can interact with some of the water particles. And then finally, our third step, we get some attractive forces between the solute and the solvent, and solvation occurs. So solvation is the formation of our solution. So we establish some attractive forces between the solvent and the solute, and we establish and we make our solution. So the first two steps of this forming a solution are endothermic. We have to put energy in because we're trying to overcome those intermolecular forces. So intermolecular forces are not as strong as bonds, but it still requires energy to overcome those intermolecular forces. So if you think back to doing a reaction in thermochemistry, we talk about energy has to be put in to break bonds, and then we release energy when we form bonds. Intermolecular forces, as we said, are not as strong as bonds, but it's kind of the same principle. We have to put in energy to overcome the intermolecular forces. And then step 3, when we're forming those attractive forces between the solute and solvent, that's kind of like we're forming new bonds, except we're forming new intermolecular forces. So this step is exothermic. So the enthalpy change that's associated with the formation of a solution is the sum of the enthalpy values for steps 1 and 2 and step 3. So steps 1 and 2, remember we said are endothermic, which means that they're going to be positive. And step 3 is exothermic, which means its sign for delta H is going to be negative. But it depends on the size of these delta H values as to whether delta H for the solution is going to be positive or negative. So if these two values are larger compared to the third delta H, which is our formation of the solution, then delta H of solution is positive. If delta H for our third step, our solution formula, is larger compared to the first two steps, then our delta H solution is going to be negative. So how do we predict whether or not we can form a solution? We know that there are some things that don't mix together, and we know that there are some things that are insoluble in other compounds. So how do we predict whether or not a solution will form? Well, there's a few factors that predict whether or not we can form a solution. The first thing is that obviously we have to put the solute and the solvent together. I mean, if we got them in separate places, we really can't form a solution. So we have to put the solute and the solvent in the same container. The second thing is that processes that take a large amount of energy tend not to occur. They tend to not be very favorable. It typically takes some outside force to cause those to occur, and usually it requires us adding a large amount of heat or a large amount of energy in order to force that process to occur, but they don't occur very readily or very easily. And then the last thing we'll think about here is that light dissolves light. So in other words, polar substances dissolve in other polar substances, and non-polar substances dissolve in non-polar substances. And ionic compounds can also dissolve, sometimes in polar solvents. So once we get our solution prepared, there are actually several properties of solutions that we want to talk about. In this video, we're going to talk about whether or not a solution is an electrolyte. So electrolytes are things that dissolve in water to produce a solution that is capable of conducting electricity. And we can break electrolytes down into strong electrolytes, weak electrolytes, and another category called non-electrolytes, which means that they don't conduct at all. So acids and bases are also electrolytes, and we're going to talk about what distinguishes a strong electrolyte from a weak electrolyte. If we look down at the bottom here, we've got a couple of examples. We're told potassium chloride is a strong electrolyte, whereas acetic acid is a weak electrolyte. So the question is, what distinguishes these two? What makes one of them strong and one of them weak? Well, if we look at how much potassium chloride is left in a molecular form, it's a very small amount compared to the amount of the percentage of potassium and chlorine ions that we have. Whereas if we look at acetic acid, we find that 99% of the acetic acid is still in the molecular form, and only about 1% has dissociated into H plus ions and acetate ions. So the major difference between these two is how much they've dissociated. In solution. The strong electrolyte is dissociated a lot. The weak electrolyte does not dissociate very much at all. So if we define strong electrolytes are dissociate nearly 100% into ions. Not quite 100%, because very little, if anything, is actually 100% dissociated. But fairly close, 98-99%. And they conduct electricity or current efficiently. So for example, if we put something like sodium chloride in solution, that breaks apart nearly 100% into its sodium ions and chlorine ions. So if you set up an electrical circuit here, what you'll find is that if you put a light bulb as part of that circuit, it's going to be lit up very brightly. So some examples of things that are strong electrolytes: sodium chloride, or really any of our ionic substances that are soluble; nitric acid or hydrochloric acid, so really any of our strong acids. So our strong electrolytes are going to be our soluble ionic compounds and our strong acids. Weak electrolytes are things that only partially dissociate in solution. So they're slightly conductive. If you hook them up to an electrical circuit, you get a little bit of electricity going through there, but not enough to light the light bulb up brightly like it was in the last slide. So if we do things like our weak acid, acetic acid, remember we said that most of acetic acid was still in molecular form, and we only have a very small amount that's dissociated. So we get a little bit of the dissociated form, enough to get a little bit of current going, but not very much at all. So things like vinegar, which is an aqueous solution of acetic acid, or our other weak acids, are going to be good weak electrolytes. Tap water is also a weak electrolyte, because tap water has some ions dissolved in there. Typically, most cities and towns have fluorine in their water. Sometimes you'll have things like magnesium or calcium in there. So you have enough ions for tap water to be a weak electrolyte, but it's not going to be very strong of an electrolyte. Also, some of our ionic compounds that are not very soluble but will produce a small amount of ions will also be weak electrolytes. But things that are highly soluble are going to be strong electrolytes. Non-electrolytes are going to be formed when we have substances that don't break apart into ions. If we don't form any ions, we have no way to conduct electrical current. So things like sugar or ethanol or ethylene glycol, which is antifreeze. So if you put something like sugar in water, it will appear to dissolve, but it doesn't actually produce any ions. So there's no ions, we can't get any electrical current going, so our light bulb doesn't light up at all. Something like ethanol mixes with water, It's polar, so it will mix with water because water is also polar. But we're not actually going to form any ions. So we can't get any current going. The same thing with ethylene glycol. We don't produce any ions, so we can't get any current going. So to be an electrolyte, we have to produce some ions. If a substance breaks apart nearly 100% into its ions, it's going to be a strong electrolyte. If it doesn't break down very much, it's going to be a weak electrolyte. And if it doesn't produce any ions at all, it's a non-electrolyte. So we will stop here, and we will get into some more properties of solutions in later videos. And I will see you in class.